aerosol effects. And several representation of ice and other things that we know need improvement. I'll talk a little bit about those. But another key aspect is increasing the resolution of the model. And that requires more computational resources. And that's where the Exascale and Petascale particularly come in, because it's allowing us to change the resolution in ways we couldn't even consider before. So, meeting all these objectives that we need to have, this can't be accomplished with current systems. That's why we need to go from Petascale to Exascale. This is just a representation of all those different components of the Earth system model that we need to consider, and then enhanced treatment of those components are going to be necessary as we look at our enhanced understanding we need for the future to be able to provide policymakers a better understanding. We're already seeing some aspects of that as we do make improvements in the model. The CAM5 is the atmospheric module in CESM, the latest version. The 5 denotes that it has microscale representation of aerosol and cloud processes that were not in the previous models. And this graph, which I didn't realize how clear it was in the distance, does do a much better job in comparison for things like looking at El Nino events and the energy in an El Nino event compared with previous models. And we can see that even more clearly that we compare the CAM5 version of CESM with the older models, which were called the Community Climate System Model, before they changed the name to our system model, 4 and 3. And we generally, when compared to the observations on the left, the new model does a much, much better job of representing the right timing and duration of an El Nino event, or rainfall events in general, El Nino and La Nina events, compared to earlier versions of the model. Another key aspect with the new CAM5 is that it does a much better job in dealing with dry zone biases, which means those parts of the world which tend to be extremely dry and capturing those subtropical dry zones. The CAM5 model, as shown in the lower right, compared to the observations, does a much, much better job than the earlier models. And a lot of that is because of the improvements in treating clouds and aerosol processes and their interactions. Should start automatically, but it's not. We also find that as we increase the resolution of the model, that we start capturing physics that we could not fully capture before. And this shows an example of looking at precipitable water for a version of the model. This is an earlier version of the model, CAM4, that was run at 1/8 of a degree. This is we're running at 1/4 of a degree on blue waters right now. It was run for a relatively short period of time, but in doing so, you found, as you can see on the central right and side here, that it can capture the production of typhoons and hurricanes much better than you could with a lower resolution model. So to capture those kind of large events more accurately, we need to go to extremely high resolution. Well, to go to that kind of resolution, we need to change the central core of the model, the dynamical core, the way the model is written onto the Earth's sphere. And we've got a transition over the years as the resolution has changed in the CESM and its predecessors, from going particularly from finite volume, which we ran at for quite a long time, to the new model, such as we're running here at Blue Waters, the home spectral element approach, that will allow us to go to about 1/4 degree. It might be able to take us to about 1/8 of a degree, but perhaps not beyond that. And eventually we want to be running a 1 to 2 kilometer resolution, and I'll talk about that shortly. And so the newest approach is called MPAS, and I never remember the form, triodal or something like that, scheme that's involved there. That's the grid on the right-hand side with the black around the Earth that allows allows us to be able to actually go to non-hydrostatic, which means we're no longer making the hydrostatic assumption in the equations of motion, so that we can go down to extremely high resolution and be able to get down to those few kilometer kind of scales where we can actually capture cloud processes without having to parameterize them. So as we think about Exascale and the kind of problems we want to run in the future, we know that the current models running at a 1 degree resolution typically cannot capture the detail at the regional scale, what's going on in specific locations in the US, for example, that we want to have a better understanding of. And therefore, we're going to need to go down to a much higher resolution, 1/4 of a degree or 1/10 of a degree. Eventually, 1/10 of a degree or better will probably be the standard. We're going to get a lot of increased accuracy. Show you just a sense of that. I could show you a whole lot more slides of what increased resolution does for you. And as a result, we'll be able to get a much better understanding of the potential impacts of climate down to the scale that humans and natural systems really care about, the impacts on ecosystems. As part of that, we also need to run a large number of ensembles because we want to account for, which means a large number of runs for any given problem, because we want to detect the signal relative to the natural variability. And we can do that is by doing a number of runs that give you different representations of that natural variability at any given time, and then you can look at the not only that range, but detect what real signal is coming out of that due to the human forcing that is occurring. So large ensembles are important because they help us to robustly determine simulated natural variability. They allow us to better assess this question of climate extremes that I mentioned, particularly at specific locations, and their changing likelihood, and to investigate detection and attribution of climate changes in the 20th and 21st centuries that we can then associate from human activities relative to those natural variations that we see in the climate system. As part of that, eventually, we're going to want to go to models that can fully resolve cloud processes. To do that, we need to get down to 1 to 2 kilometer resolution, where the cloud's physics can be represented accurately, and we get away from the parameterizations that we currently have to use. And for that, we're definitely going to require Exascale. This shows the kind of, with just looking at the physical resolution of the model, as you go from 200 kilometer resolution, which is the kind of models we have used even in the current IPCC assessment. Previous models, or the previous assessment, standardly used the 2 degree or 200 kilometer resolution. We're currently running in blue waters at the 25 kilometer resolution. And this is showing the West Coast. And what we want to get to eventually is to the point where we can really capture in great detail what is going on with the mountains and other parts of the orography in places like California, which is what this is showing. So looking at Exascale, what kind of problems would we want to run on that? Well, I'll give you some hints about that already. Obviously, we're going to want to run analyses of climate change and projections going out in the future. This century and likely well beyond this century, climate change does not end at 2100, even though we intended only to go into graphics up to that point. Those analyses can be fully coupled, where we include all aspects of the climate system. We're going to run 200, 400 years or more in length. The inputs will be time dependent. We'll look at a range of different future emission scenarios, large number of ensembles, and to do that, we're going to have machines like Exascale to really get there. At the same time, one of the biggest problems in the weather climate community right now is this time period between the weather scales that are roughly, and we can now predict the weather roughly out about a week, and we can project climate changes out over the next 20 years or so. but we do a very poor job in understanding what's likely to happen in the next decade. And yet that's extremely important to farmers and others that would really like to know that information. You know, what's the weather likely to be like a year from now, so they could do a better analysis of how they should plant their crops, et cetera. Well, weather forecasting is generally done as an initial value problem. It's how well you know the initial conditions that allow you to go up a week. And eventually, the ultimate is to get out about 2 weeks and then before chaos and the system takes over. Climate modeling is typically a boundary value problem. We're trying to look at long-term timescales and look at how the climate is changing over those timescales. We need to understand how those changes, you know, what kind of changes we might experience over a decade or less timescale, and that's going to require a very different way of thinking. That's where I think is the exciting area of research. If I look at weather climate analyses over the next decade, that's where I would be putting my efforts. I'm probably going to retire before that happens, but eventually, I think this is really important. And to do that, we're going to have a much better understanding of the ocean cycles and what roles they play in year-to-year weather, et cetera, and as we try to do that. And so it becomes a very difficult problem to have the right initial data in the model to be able to make this happen. There's going to be a large number of ensembles, very high resolution again, to be able to do those analyses. Again, they're going to need Exascale. We'd also like to go back over that 2,000-year time period, or perhaps much longer. It'd be really interesting to go back to 20,000-year time period to the end of the last ice age, for example. Or to look at some of the previous interglacial time periods. But we have a lot less understanding of those than we do the last 20,000 years. And to do that, again, it's going to this kind of very long timescale analyses are going to, again, require exascale machines. So as we look at the needs for computing resources over this next decade, the increased complexity of the models as we improve the physics, the chemistry, and the representation of biology in those models, how we represent all land use changes and all kinds of things, are going to put a requirement on that. Going to higher resolution is going to put a requirement on that. How we better assimilate satellite data to put another requirement on our needs. And then the duration of the runs and the ensemble sizes also puts another. And so we're likely to see a significant increase in computational resources towards really understanding our Earth's climate system and how it's likely to change. For computer scientists, this represents critical challenges to address scalability, programmability, resilience. We got the power needs of the machine itself that is going to require some special thinking. I'm going to talk about that in just a second because there's some interesting work at LBL related to that. And certainly concerns about I/O and memory, putting out huge numbers of output data that we really don't even know how to analyze. Weiner et al. A couple years ago, and it continues to work on this at LBL, has been looking at the question of should we be taking an alternative approach to how we design exascale type machines? Should they not just be based on having a hardware that can generally be applied to all types of problems, like Blue Waters is a Petascale machine, but should we actually be designing machines that are designed for the specific problem at hand? And so to quote from that paper, we need to design machines to answer specific scientific questions rather than limit our questions by the available machines. So it's something to think about, and something I think we all need to much more thought about as we look to the future. And that raises big questions about the power requirements of an exascale machine, and that perhaps we need to go this route in order to reduce the power needs for answering specific science questions. So I thank you, and I'll be happy to address any questions you have.
Any questions?
How do you address the success of a model? Like, how do you evaluate when the model is considered successful? Is this proscriptive? Do we use older data and predict what comes to date, or do we predict in the future and wait and see? Or?
No, we base those analysis on looking at lots of processes first at the small scale. You can pull out the different parameterizations or processes in the model and look at specific questions where you have very detailed measurements. But then on a little bit larger scale, the model itself, then you could look at what kind of data do we have globally that we can look at both in the oceans, in the atmosphere, and the biosphere that we can compare with. And very, very detailed analyses are done to look at that. But we still have an uncertainty. If we look at what's called the climate sensitivity factor, which is something that was developed years ago for just doubling the amount of carbon dioxide from pre-industrial levels, about 300 parts per million to 600 parts per million. That climate sensitivity has remained essentially unchanged over the last 30 years, from 1.5 degrees Kelvin or centigrade to 4.5 degrees centigrade. And you can find different data in the past that support either end. And the models tend to support that range. And we have not reduced that uncertainty, because if we gain more understanding, we also gain more uncertainty. And so it's just part of the process. But we try to do very careful analysis. And some things the models do extremely well on. It really does look like Earth when we look at the model. But it's not a perfect Earth. And we know there's some things that we don't represent well. We know some things like clouds and precipitation patterns, the models tend to do poorly. And then they will greatly improve those as we increase the resolution. That's a no.
Could you give us an idea about the size of data you're using? How do you associate the data, where they come from? How do you set up the initial problem? It's not I see it's data is the key for most every source equation. Anybody can solve almost anybody can solve any source equation. But how do you look at this data? I guess you have satellites, you have aircrafts, you have balloons, and so on and so forth.
Right. So the question is, how do we use many large amount of data sets that we have to consider? Most of it, the model basically starts out with the solar input and derives the atmosphere and the oceans and so forth. The one exception to that is subgrid scale. So anything less than the 1 degree or the quarter of a degree or whatever we're running at that we need to consider, we will need to have a parameterization based on a large amount of observations of things like clouds that have been used to develop that parameterization. But the model basically derives everything else, and then we extensively compare with the satellite observation data sets. But we don't use them initially. We'll have an initial condition that's based off of a previous model run usually. But it's not, you're not dependent on those data sets for really running the initial model. It's more for the comparison.
What's the size of your
Now, that's not true of the weather models. I mean, they're entirely dependent on that initial condition.
So what's the size of your model in terms of resolution?
I was trying to think. It's hundreds of thousands of lines of code, and I don't remember exactly what the. So we're running at quarter degree on blue waters with 150,000 processors. I think we can run a year roughly every 4 or 5 days. So it's a big animal. I just don't remember the exact size. I should know that.
One last question. In the news, they said the European models are better than the American models.
Certainly for weather, that has been the case lately. And that is because of medium-range forecasts, the European model's been doing a somewhat better job than the American models. A lot of that has to do with computational power. NOAA has not received an increase in its computational power large enough compared to the Europeans in the last 4 or 5 years, or a decade. And as a result, we've fallen a little behind the resolution. If they can run their weather models, they have. In terms of the climate models, the U.S. models are amongst the very best. And there's some good European ones. There's a Japanese one that's very good. And there's 3 really good ones